Special relativity is a fundamental theory of space and time.
Developed by Albert Einstein as a modification of Galilean theories on perception.
Explains experimental issues with lightning and involves light and electrodynamics.
Einstein postulated that the speed of light in free space is the same for all observers, regardless of their motion relative to the light source.
Imagine two observers, one seated in the center of a speeding train car, and another standing on the platform as the train races by. As the center of the car passes the observer on the platform, he sees two bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time, so he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to his eyes at the same speed, the speed of light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear. But what does the passenger see? As her friend on the platform predicted, the passenger does notice the flash from the front before the flash from the rear. But her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct? The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike? Einstein tells us that both are correct, within their own frame of reference. This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity.
Oh, hello there. Consider an approximation of the theory of general relativity valid for a weak gravitational field.
It also predicts a nonlinear velocity addition formula which prevents speeds greater than that of light from being observed.
Which joins space and time into a unified four-dimensional continuum called space-time.
Then there are the postulates of special relativity. The first postulate states that the laws of physics are the same in all inertial frames of reference. The second postulate states that the speed of the light in the vacuum is independent of the motion of the light source.
Imagine the great scientist in a rocket ship, floating in deep space. The ship has powerful headlights, and when Albert switches them on, the light races away from him at, of course, the speed of light, 670 million miles an hour. Now imagine that Albert has a twin brother, Bertrand, who also has a spaceship. Let's say Bertrand flies away from Albert at half the speed of light. When Albert turns on his headlights, how fast would they seem to be going when they overtake Bertrand? You'd think he would see them pass by relatively slowly, like a faster car passing you on the highway. But that's not the way light works. Instead, Bertrand would see Albert's high beams pass him at the full speed of light. Bertrand's own speed makes absolutely no difference.
This prediction of Einstein that the speed of light is the same for everyone is one of the strangest in physics. But it's true. It's been shown by hundreds of experiments. The speed of light is going to be the same, no matter how fast you're moving towards it or away from it.
Even if Bertrand turns around and travels head-on towards Albert, he would still see Albert's headlights pass him at the same speed. So what's going on? Welcome to the realm of time travel. If both brothers see light moving at the same speed, then something else must be changing. That something is time.
Something has to give, and the things that have to give are space and time. It turns out that if an object is moving fast enough through space, it can alter its passage through time.
at 5 miles per hour, and Justin's car is moving at 10 miles per hour. So to me, the viewer, his car is moving 10 miles per hour, but to Ben, the runner, the car is moving at 5 miles per hour.
Oh, he's an idiot. If I throw a ball in the car, it's only moving at the speed that I throw it.
From a bystander point of view, the ball is moving at the speed of the car and the speed that I throw it at.
So in a car, you feel like you're just sitting still. So you can do regular actions in a car and the motion won't affect it, like pouring water. If we were to turn, however, if we turn sharp left, I would probably spill it, or spill out of the cup right.